Welcome back to another video. This is a heat conduction in a rod with different temperature boundary conditions. This is example 2, sorry. Example 2. So, in the last one we found the steady state solution and then the transient, and then we added them together, right? Because remember, right? So let's look at part A. Let the ends of a copper rod, keep that in mind, copper rod, 100 centimeters long, to be maintained at 0 degrees Celsius. Okay, suppose that the center of the bar is heated to 100 degrees Celsius by an external heat source, and that the situation is maintained until a steady state results. Find the steady state temperature distribution. So this is an interesting case, isn't it? We have the two ends are at 0, but the center is being heated. So what would we do in this case? Well, you can split the rod in half. So what we're going to do is we're going to split the rod in half. We're also going to split the problem in half. Where we know this side of the rod, we're going to go from 0 to 50, because 50 is where the other source is, and then this one goes from 50 to 100. Okay, so we know that u of 0 of t, because we have 3 boundary conditions basically. That's why I'm splitting the rod in half. We have 3 boundary conditions. We use that same boundary condition over here with the other end. See how I split that up? So now u of x naught is equal to f of x. Does it give us an f of x? No, it does not, right? So if it doesn't give us an f of x, we're just gonna keep it like this, right? It just wants us to find a steady state temperature distribution. So that's all we have to do for this one. What was I doing? Alright, let's keep going with this one here. So we know the heat equation. Sorry, XX. This notation that I made up is killing me here. Okay, we know this is 0. That means that goes to 0. So then right, where was I? Yep, so then u of s is equal to, remember, c1 plus c2x. Solve the characteristic equation from this. Through our boundary conditions, c1 is 0. This was 100, right? The center? Yeah. 0 plus c2, 100 c2. c2 is equal to 1. Or wait. It should be 50. Yeah. c2 is equal to 2. So then u of s is equal to 2x for that case. Over here, we have same scenario. This is going to be exactly the same. It doesn't give us anything. So we have two equations here, two unknowns. I guess we have to solve a little system here. So what can we do here? We can solve this one for C1, the first one. 100 minus 50 C2. Plug that into this one. And then we will get 100 minus 50 C2 plus 100 C2 equals 0. 100 plus 50 C2. It's negative 2, right? C2 is negative 2. 100 plus 100 is 200, so C1 is 200. And then our U of S of X is going to be a piecewise function. Uh, 200 minus 2x, right? Oh, this includes 50. Includes the center. So here's the answer to part A, the steady state distribution. Now, looking at part B, I think they want to actually solve the PDE now. At a time t0, after the steady state has been reached, let the heat source be removed. So then the 100 Celsius at the center gets removed. Okay. At the same instant, at 0, the end at 0 is placed in thermal contact with a reservoir at 20, while the other one remains at 0. It sounds like we're going to have some new boundary conditions here, aren't we? So we know we're starting from the steady state conditions that were given here. So guess what? That's going to now be our f of x, right? So now u of s of x is going to be our initial condition. U of x 0, right? Excuse me. Our new boundary conditions. We only have two ends to worry about now. One of them is 20. The other one is 0. So now we have to do this again. I'm sorry. We have to find them all over again, right? Okay, so let's find the steady state solution. So we know it's, we're just going to skip right to here. First boundary condition, 0 is 0. Hundred. Both are equal to 0, so no, wait, something's not right. Something isn't not right there. Isn't that equal to 20? Oh yeah. It says it's not placed in a reservoir. Sorry, it was at 0 before. I'm sorry. Now it's in a reservoir at 20 degrees Celsius. I forgot about that. Okay. I was gonna say, that doesn't make sense. Why would they make me do that? Okay, so it's 20 plus 100 C2, which makes a lot more sense. So then that's negative, negative 1/5. So now we can solve for the rest of this. Just move that over. Rewrote it. What was I doing? Right. So then we do our two. We find our new boundary conditions and initial conditions. So we have. They should both be 0 for the transient solution. So we have u of t of 0t is going to be u of 0t, which was 20, minus us of 0, which is also 20, right? That's 0. U of t of 100t was, I don't remember what that one was. So that one's 0. That one's 0. Minus u of s of, yeah, that one's also 0. Okay. Yeah, so that works. Both 0. U of t. The initial condition, right? That's just f of x minus. So it's u of x naught, which is the steady state from the last problem. So, except we're also adding on now this. No, wait. Oh yeah, this is the new one. Sorry. So it's gonna be ut x0 11/5. No wait. 2x plus 20 minus 1/5 x. I believe. That is equal to 2 minus 1/5. 9/5. Oh boy, something's not right here. Oh, I see what I did wrong here. First of all, I forgot to write out u of s. This would be minus because I'm subtracting it, right? So it's 11/5. So that is 2x, 11/5 x minus 20. And then we have 200 minus 20, which is 180. Minus 2x. So that's that, which is negative 9/5 x. Alright, so this is our new transient initial condition. Now, from previous heat conduction problems, we know the general solution is this. The length squared is 100 squared, right? Over the length. That's what, 10,000? So then our B sub n is going to be 800, well, 2 over 100 times, remember I'm doing the half range expansion, 0 to 50, 11 over 5x minus 20 times sine of n pi over 100x plus 2 over 100 integral 50 to 100 to 20 minus 9, oh no, 180, sorry, minus 9/5 x times sine n pi, I'm out of space, n pi over 100 x. I am not going to integrate that again because I've done it just earlier today before when I was doing this problem, and I don't feel like doing it again right now. So here, you know what? I'll post a picture on here of the integration. Here's a picture of the integration that I got from my book Solution. But I hope that they're right on this one, because I'm obviously not checking it, but this way you guys your answer. I don't feel like integrating it at the moment, because this isn't an integration course, this is a diffie-q course. But B sub n is 800 over n squared pi squared sine of n pi over 2 plus 200 over n pi cosine of n pi minus 200 over n pi cosine n pi over 2 minus 40 over n pi. Alright, so I went ahead and I pulled out our little simplification sheet here from the video I made on Fourier series simplifications, because I didn't remember them, to be honest with you, for this one. So you can see here, we know what cosine of n pi is, of course. We can easily rewrite that one. As you can see here, we have an interesting simplification going on here. This is going to be kind of difficult. This is one of those cases where I might just leave it as it is. But let's try and simplify this. I've never done this before. Now I know you can see the sine of n pi over 2 can be written for n even or n odd, but so could the cosine. You can split it up. Here's what I'm gonna do. I'm gonna create some new notation. In this case, we can keep this like this. Yeah, let's just keep this like this. Oh, sorry, this is odd. This is even. So after further interpretation, I realized that I haven't gaslit by my book's friggin' answer. This is incorrect. This should be over 2. Actually, it looks like this solution is completely incorrect. This integration here. Let me find the correct solution here. Yeah, okay. Here's the correct integration. This is what I'm like. But they're already applying the odd case into here though, which is a problem. Because so they're skipping steps there. So let's see. Maybe I am gonna actually get stuck friggin' doing this. Sorry I'm wasting time here, but let me see something here. Let's ignore this step for right now. Let's just go from this step here and forward. Oh, actually, hold on. I see what they did there. Yeah, they just do the integral from 0 to 50. It's that. I can believe that. They do the other side. Yeah. This actually makes perfect sense. I see how those are going to cancel. But if you plug in the 50, that's pi over 2. That's pi over 2. This is just n pi. Oh my lord. What's going on with that one cosine term? I'm confused. Let's write this out. That's also pi over 2 and pi over 2. And we have plus. That's just n pi cosine. That's just n pi. That's also. Oh, I see. That guy must have evaluated it wrong before. See, that one disappears because it's 900 minus 900. Okay, see? Never trust the internet. And this is also 0 because it's going to be sine of n pi. So these two terms are 0. That's 0. That's 0. And then we're just left with those two terms up there, right? I think so. I should be right. How come, oh, well, we're missing a term here, so. Because 150. Oh, god damn it. I forgot the second half of all the. Plug a 0 in. Mm-hmm. And the other term's just 0, so. There is that. It should be negative, though, apparently. That doesn't make any sense to me. Oh, yeah, because yeah, okay, makes sense. What I'm not seeing here is where that 500 goes. I mean, where that n pi over 2 goes. We're also going to have a minus 1 over 50. This is 50 now, so this is cosine pi over 2. Or maybe this cancels out with that one. Pi over 2 n pi over 2. There's 900. Minus 9 times 50. Okay. Minus, you can see why I didn't want to integrate this one. Here I am, still evaluating it. Okay, 18,000. Pi squared n squared times sine of n pi over 2. That should be, yeah, okay, that's good. So now let's see here. This becomes 1 over 50 times, well, let's calculate that. Bust out my calculator. Negative 20. Negative 20, thank you. Times 11 times 50. Minus 100. I'm getting negative 9,000. Okay, well, I'm getting, we'll see if that's right. Well, what's that divided by 50? 44. N pi over 2. And then minus yeah, it doesn't make any sense. It's supposed to be 40. Oh, times 100. Oh my lord, I forgot the 100 in there. Okay. Yeah, that is 40. Perfect. And then we have plus, maybe it's not plus. What's 900 minus 9 times 50? It's 450. So yeah, it is going to be plus 450 times 20. 9,000 divided by 50 is 180. Would you look at that? Would you look at that? Then we have minus 18,000 divided by 50. 360. Oh my god, that's beautiful. I think it is. It's supposed to be equal 800. Wait a minute. Shouldn't this be 440? That should be 440. Wait, let me check. Let me double check that really quick. Which one is that? 20200. Is that 22,000? Oh, it's 22,000. Yeah, it is 440. Okay. Divided by 50. Yeah, 440. Minus 6. What did I say this was? What did I say that was? 100 divided by 50, 360. Pi squared n squared. Sine of n pi over 2. See why I skipped all those beginning steps? These problems take forever sometimes. Okay, these obviously cancel. Those are gonna, that should be positive. Yes, it should be because the negative on the outside. And then we're left with 800 over n squared pi squared sine n pi over 2 minus 40 over n pi. Now I notice my textbook, and either does this guy, they don't simplify any further. But I am a high achieving individual, and I want to simplify this, even though it doesn't get rid of the sine term, you know? So let's do for n odd. It's 800 over n squared pi squared negative 1 to the n minus 1 over 2 minus 40 over n pi. So let's go ahead and write this out. This is our u of t. Well, let's do the whole thing. What was the first part? What was u of s? 20 minus 1/5 x? X over 5 plus the sum. Oh, this is n odd. And n odd is equal, oh my lord, it's 2n minus 1, correct? That's always odd, I think. Let me see, if this is 2, 4 minus 1 is, yep, that's always odd, okay. So then we're going to plug in every n as being this. So this leaves us with, I don't know if that's any more simple. Yeah, that might even be more complicated. 2n minus 1 is 2n minus 2 over 2 minus 40 over n pi. So you can do that, or just leave it as 800, sorry, n squared pi squared sine n pi over 2 minus 40 over n pi. I just realized that should be that way. Okay. So, yeah, that's that. That's the answer. Oh man, I was losing my mind on that one. I got gaslit by the internet. There's internet solutions. Textbooks, those is the Quizlet textbook solutions. They're not always correct. I've learned that today. So here's the correct answer. Now let me see what we're doing next after this. After this is, I think it gets a little bit easier for a one section. Oh yes, the rod with insulated ends. So now we're going to be looking at a rod that has Newman boundary conditions or insulated boundary conditions at the ends of the rod. So they're like derivative boundary conditions at the ends. So it's going to get slightly easier, I think, for a little bit. However, because of this change, we're going to have to redo our boundary value problem now, because now we don't have two Dirichlet boundary problems. We're going to have to redo the whole process now, which is going to suck. But what can you do? So I will see you next time for that video.